Hello, Binomial Theorem fans. We are going to do some expansions today, and we're going to start with this, what looks relatively mild expansion, 5 minus 2y to the third. If you've researched your binomial theorem or paid attention in class, we now know that we can do this through a process of expansion, and I'm going to use there's a lot of ways to talk about combinations. Combination NR is often written as, and this is the way your calculator likes it, NCR. And there's also a notation like this. And just for the sake of space, I'm going to use this form. So to expand this binomial to the third, I'm going to be interested in the exponent, and my first term is going to be combination 30 times our full allotment of fives. That would be 5 to the third times, and you wouldn't necessarily have to enter this term, but I think it helps us see what's going on, our negative 2y's, but 0 of those. Now here's an important thing to remember as you're going. These two entries right here, our exponents, as we're expanding, should always be adding up to our 3 or our 3 exponent here. These guys should always add up to that as we expand. Second term becomes C3, 1. And then we reduce our 5's, 5 to the second, as we increase our negative 2y's. Negative 2y to the first. And we continue on that. So our following term would be C, or combination 3, 2. Decrease our 5's, 5 to the first, increase our negative 2y's. Negative 2y to the second. Notice again, our exponents still add up to our 3. And we exhaust this with our final term, C3, 3. We're no longer using 5, so 5 to the 0th is 1. We wouldn't have to include that there. But our full allotment of negative 2y's. And now we just have a little cleaning up here. To find C30, C31, C32, C33, we can go through the combination process, but we can also use the third row of Pascal's triangle as well. C30 in a real world problem means how many groups of 0 can I choose from 3? It's just 1, but Pascal's triangle reveals that as well. So our first term becomes 1 times 5 to the third, 125, times negative 2y to the 0th, 1. Plus our second term, C31 is 3. How many groups of 1 can I choose from 3? 3 times 5 to the second, 25, times 1 negative 2y. Plus our third term, C32 is also 3, times a single 5, but negative 2y squared positive 4y squared. Plus C33, how many groups of 3 can I choose out of a group of 3? Just 1. Times 5 to the 0th, 1. Times, again, the full allotment of negative 2y's, negative 2y to the third, negative 8y cubed. Giving us a final simplified result of 100 25. Here I have a plus times a minus, so minus 3 times 25 times 2, 150 y. Next term, 3 times 5 times 4, or 15 times 4, plus 60 y squareds. And our final term, 1 times 1 times negative 8, so minus 8y cubed. So there is our binomial expansion, simplified. Okay, problem number 38 is a binomial theorem expansion on a fifth degree binomial. So we're going to have a little bit of space here, but we're going to start here with our combination work. And of course, our first term always starts combination, our exponent 0, C5, 0. Then we use our full allotment of 2x to the thirds. So I've got 2x to the third, all of that to the fifth, but I don't need to use any y's here. My next factor in this term would be negative y to the 0th. So I just move on down the line. Next term becomes C5, 1. I reduce my number of 2x to the thirds. So 2x to the third, now only using 4 of those. And my fifth factor, see there'll always be 5 factors, my fifth factor here is going to be 1 of the negative y's. Negative y to the first. Easy enough. And we just continue with this progression. Plus C5, 2 times how many 2x to the thirds? Right, 3. But if I have 3 of these, I need to have 2 of these. So I need 2 of my negative y's. Plus C5, 3, decreasing my 2x to the cubes yet again. 2x cubed. Now we're down to a pair of those. So we need to balance that with 3 of the negative y factors. Plus C5, 4. And 2x to the third's down to just a single one of those. 2x to the third, but 4 negative y's. Until I wrap up with C5, 5. Don't need any 2x to the thirds here, but I need all of my possible negative y's. So there's our expansion. No one hard thing, just a lot of easy things. So a lot of opportunities for little calculation mistakes here, but we're going to be careful. To find my combinations on 5, I could go to fifth row of Pascal's triangle, or I could enter C5's, C5, 1, C5, 2 into our calculator and such. But I'm going to be using from my memory Pascal's triangle. C anything 0 is 1, so my first term becomes 1 times, I need 2 to the fifth, that's 32, and I need 5 groups of 3x's, 5 groups of 3, 15x's. Plus, C anything 1 is the top number. So C7, 1 would be 7, C12, 1, 12, Cn1, and C5, 1, 5. Times 2 to the fourth, 16, x to the 12th, and a negative y, which is going to make my second entire term negative. Plus C5-2, if you don't know anything about combinations and I put 10 down here, you're going to think we just multiply the numbers right now, but that's, of course, not how we find combinations. C5-2 is 10. I need 2 to the third, 8. I need x to the third, x to the ninth, and I need a pair of negative y's, but of course that's just positive y squared, plus C5-3, 10. See, I told you we don't just multiply them, times a pair of 2's, 4, a pair of x to the thirds, x to the sixth, and 3 negative y's, which makes this term negative, plus C5-4. C5-4 is 5 times 2x cubed times negative y to the fourth. The y gets absorbed, or the negative gets absorbed, excuse me, y to the fourth, plus C5-5, 1. How many groups of 5 can I get from a group of 5? Just 1. Times negative y to the fifth. All right, so a little calculator work here perhaps. 32x to the 15th. My next term, I've got a plus, but ultimately times a minus, is going to be minus 5 times 16, 80, x 12s, and a single y. My next term, plus 10 times 8, another 80. This time, x to the ninth, y to the second. My next term starts out positive, but ultimately gets multiplied by a negative. So you see, we toggle back and forth between plus and minuses here. I get 10 times 4, 40, x 6, and y to the third. My following term, plus 10, x to the third, y to the fourth. And I need to buy a little wider smartboard. And my final term, plus times minus minus y to the fifth. So there is our fifth degree expansion. Notice we end up with 1, 2, 3, 4, 5, 6 terms, not just 5 terms. Okay. Here's a binomial expansion to the 7th degree. That's going to be a beast, except they're merciful enough to just ask for the 4th term in the expansion. And we just have to figure out what are we going to look like by the time we get to the 4th term. If we started our expansion as if we were going to do the entire expansion, we would start with C7, with some factors. C7, would be our second term. C7-2 is our third term, and C7-3 is our all-important fourth term. Now here's something worth noting. Hopefully at this stage we know that C7-7 is equal to C7-0. C7-6 is equal to C7-1. Combination 7-5 equals combination 7-2. And more importantly for this problem, combination 7-4 is combination 7-3. We can actually use combination 7-4, with n being given as 4. So I'm going to set this up as combination 7-4, but I want to check how many x's I need. I know I need some x's, and I know I need some negative 10z factors. So x's, I would need 7 x's here, 6, 5, 4. There we go. There's our 4. There's our n value popping up again. So how many negative 10 z factors do I need? I need to make up the difference from 7 to 4. I need 3 of those. Okay. Now, as far as C74 goes, that's combination 7-4. We could do that on our calculator. We could use Pascal's triangle. Heaven forbid, we could do it by hand if we were stranded on a desert island and had to buy coconuts by solving combinations for the natives. But we're going to go ahead and do this one with, I'm just going to pull a Pascal's triangle number off, and this is 35. I've got an x to the fourth. I've got negative to the third, negative survives to the third, 10 to the third, 1,000 z to the third. So we end up with negative 35,000 x4 z to the third. Nice that we just had to find the one term. Here's a variation on a binomial expansion problem where we just need to find the coefficient a that would exist with the x to the fourth, y to the fourth. Much better than having to expand this entire binomial much quicker. So to get x to be 4, I could start with combination 8, 4. Then I would have 4 2x factors. And how many negative 3z factors? Well, my 4 and this exponent have to add up to be 8, so I need 4 of these. Combination 8, 4, you could enter in your calculator as 8c4, or you could pull it off of Pascal's triangle, or we could run that thing by hand if we were forced to. I'm going to use Pascal's triangle value. This is 70. I need 2 to the fourth, 16 x to the fourth. I need a negative to the fourth, that's a positive. I need 3 to the fourth, 81, and I need z to the fourth, which leaves me with 70 times 16 times 81, 90,720 x to the fourth, z to the fourth, which is great, but the book's really asking for what is a. 90,720. Nice break from having to expand that.